Okay, in this lecture, we now get a basic understanding of wave kinematics. This lecture is specific to conceptual physics AB. Mathematically describing individual wave pulses, whether they be transverse or longitudinal, is actually mathematically difficult to do. So then therefore, we're going to concentrate our efforts on the easiest wave to describe mathematically, and that is what is called a simple periodic wave. As I describe simple periodic waves, I'm going to be drawing it out as transverse waves, but longitudinal waves can be simple periodic waves as well. Okay, now what is a simple periodic wave? Well, very simply, each section of the medium is in simple harmonic motion. Each section of the medium is a simple harmonic oscillator, and all of those simple harmonic oscillators are slightly out of phase with respect to each other. So each section of the medium is in simple harmonic motion. Each section is a simple harmonic oscillator. Okay, now, well, what does that mean? Well, for example, let's say that I have a spring laid out like so. And then what I do is I grab a hold of the spring's end and I oscillate my hand up and down like so in simple harmonic motion. When I do, I transmit, as we say, simple periodic waves, which then propagate down the length of the spring. If I could take a picture of those waves at some moment in time, that picture then would look like this. Like so, where the waves, we'll say, are propagating in this direction with a speed v. After this short lecture, I'm going to prompt you to watch a screencast that shows the propagation of simple periodic waves. But before we do, let's examine some definitions here on this diagram. So once again, this is what the waves look like at some moment in time, if I could somehow take a picture of the spring. Okay, now mathematically, there's really no difference between the tops of the waves like so and the bottoms of the waves like so, but we do give them different names. The tops of the waves are referred to as crests, and the bottoms of the waves are referred to as troughs. The distance from crest to crest is the same thing as the distance from trough to trough, as long as the waves are simple periodic waves, and that distance is referred to as the wavelength. We always use the same Greek letter to describe the wavelength, and that's the Greek letter lambda, which is drawn in the following way. So for example, from crest to crest like so, that distance right there is referred to as lambda. This is called the wavelength. Okay, now back in terms of simple periodic motion, oscillations, we talked about frequency and period. Those definitions of frequency and period carry over here into this description of simple periodic waves. So for example, let's say that we have an observer. Let's say that observer is standing right here, and this observer times how long it takes for one wave to go by, one wavelength like so. Well, the time necessary for one wave to go by is also the same thing as the time necessary for each section of the medium to undergo a full oscillation. That's the period. So the period is the time necessary for one wavelength to go by. That's the same thing as the time necessary for one oscillation to occur. So capital T is once again referred to as the period. This is the time necessary for one wavelength to go by. And then the inverse of that, once again, is the frequency. The frequency is equal to 1 over the period. It's measured in terms of hertz. This is the number of waves that goes by per second. Number of waves per second. So recall how the two quantities, period and frequency, are related to each other. For example, let's say that the period, or rather, let's say that the frequency is 1 hertz. So then therefore 1 wave goes by per second. Therefore, what's the period, the time necessary for 1 wave to go by? Just 1 second. Let's say that the frequency is 2 hertz. So 2 waves go by per second. Therefore, what is the time necessary for 1 wave to go by? Well, it would just be a half a second. So once again, frequency and period are inverses of each other. This then allows us to describe the speed of the wave in terms of the following definition, going all the way back to introductory kinematics. Recall that speed is distance divided by time. So let's say that the waves here have a speed v. Let me draw it like so on the diagram. And speed is equal to distance divided by time. A very useful distance to use, however, when describing periodic waves is the wavelength, lambda. And then we divide that by the time necessary for 1 wavelength to go by. Well, that's just the period, capital T. So speed as distance divided by time is wavelength divided by period. More times than not, however, you'll see this little formula here not described in terms of the period, but instead described in terms of the frequency. Speed is equal to wavelength multiplied by frequency. This then describes the basic kinematics of a simple periodic wave. Okay, now what about a basic introduction to the dynamics of a simple periodic wave? In other words, if you applied F equals ma to such a situation involving a spring. It's actually a pretty complicated problem mathematically to describe. It's well beyond the scope of this course. However, if you do apply F equals ma to transverse simple periodic waves, you could actually derive an expression for the speed of the wave. The speed of a transverse wave. Now, when I describe the speed of this transverse wave, I'm not going to derive the expression. It's well beyond the scope of this course to do so mathematically. I'm just going to give you a basic understanding as to what the speed is determined by. The speed is basically determined by 2 things. Number 1, the rigidity of the medium. In other words, if I take this spring and I increase the tension in it like so, I then increase the speed of the wave that is propagating through it. I actually demonstrated this to you in my short lecture on mechanical wave pulses. I started off with the spring as being rather loose and the speed of the wave was slow. I then stretched out the spring to a greater tension and the speed of the wave increased. So in part, the speed of the wave depends upon the rigidity of the medium. Basically, the more rigid the medium, the greater the speed of the wave. But then, the speed of the wave also depends upon properties of the medium itself, specifically its density. Now, when I describe its density, I'm going to do so in terms of a one-dimensional spring. So we're just going to think of the spring as having length. We're going to ignore its thickness in this direction. In a one-dimensional case, density is referred to as linear density, and it is defined as mass over length. So not mass divided by volume for a 3-dimensional object, but instead for a 1-dimensional object, mass divided by length. The linear density, as it's called, is referred to by the Greek letter mu. The Greek letter mu is equal to mass divided by length. It's describing a basic property of the medium itself. So the speed of a transverse wave as it propagates through a spring in this manner depends upon the rigidity of the medium, the tension that's applied to it, and its linear density. Specifically, the expression itself that can be derived is that the speed v is equal to the following. It's equal to the square root of the tension divided by the linear density. Now, don't be confused. This right here is not the period. This right here is the tension that is being applied to the spring. This is describing the dynamics of the situation. In other words, if you apply F equals ma to a spring, ultimately, how does that then determine the speed? The speed ends up being this expression here. So this expression here is a dynamics expression, whereas this expression here is a kinematics expression. Okay, now let's just take a look at a basic introductory example involving these simple formulas for a simple periodic wave. Go ahead and copy that example down into your notes as I begin to read it here. We'll examine a couple of different things in the context of this example. Okay, so a student creates simple periodic waves on a spring. The student oscillates the spring back and forth with a frequency of 0.5 hertz, and the speed of the waves is 5 meters per second. So let's go ahead and access this example here. Let's go ahead and write down the numbers that were given. Okay, so the frequency of the waves, this is the same thing as the frequency of your hand moving back and forth as you transmit these waves. This is given to us as 0.5 hertz. Okay, and then the speed of the waves, v, is also given in the problem. It's given as 5 meters per second. In part A, we're asked to calculate the wavelength. So when calculating the wavelength, we're using this little kinematics expression right here. Speed equals wavelength multiplied by frequency, and now we just solve for the wavelength lambda. So divide the frequency to the denominator to the other side like so, and then we just merely have 5 meters per second divided by a half hertz. This is then therefore equal to 10 meters. So these are actually rather large waves when talking about this basic example. Okay, next in part B, we're going to calculate the period capital T. We can do so by remembering that the frequency is equal to the inverse of the period, like so. Once again, don't get confused. This capital T here is not tension. This capital T is period. So then therefore, let's go ahead and cross multiply and solve for the period. The period is equal to the reciprocal or the inverse of the frequency. So it's 1 divided by 1/2, which is equal to 2 seconds. Okay, and then lastly, we'll do a little bit of dynamics here. Let me go ahead and move my file to do so. Okay, so now in part C of the example, we're specifically going to use this dynamics expression that describes the speed of a wave. Once again, it's the speed of a transverse wave as it propagates through this spring. So let's read the following. If the linear density of the spring is 0.3 kilograms per meter, what tension is being applied to the spring? So we're given mu. Mu is equal to 0.3 kilograms per meter. We already know the speeds of these waves, 5 meters per second, and now we'll just do a little bit of math and solve for tension. So once again, this right here is not the period, this is the tension. Ultimately, this expression is derived by applying F equals ma. Okay, so let me do a little bit of erasing. I don't need this quantity here, nor do I need this stuff here. Now let's just do a little bit of math here and solve for the tension. So to solve for the tension, I need to get rid of the radical sign first. So I'm going to square both sides of the expression, like so. And now we'll just cross multiply the density here to the other side of the expression to end up in an expression here for the tension. When we calculate the tension, it's a force in terms of newtons. So then therefore, I have 0.3 kilograms per meter and then multiplied by 5 squared. And this ends up being 7.5 newtons. Once again, the greater the amount of tension applied to the spring, the greater the speed. This is a basic property associated with all mechanical waves. Basically, the greater the rigidity of the medium, the faster the speed of the propagation through it. Okay, at this point, go ahead and watch the screencast that I have posted for you that depicts the kinematics or the propagation of a simple periodic wave.